solving all these integrals and beyond up to infinity. So basically in this video I will solve literally I'll solve all of these integrals, but the way I'm going to do it is by solving this integral where these numbers are generalized by the variable n. Yeah. So now to solve this integral, what we can do is we can substitute y as x to the power n, y to the power 1 by n as x, and 1 by n y to the power 1 by n minus 1 dy as dx. Yeah. Now what do we have? The integral will still go from 0 to infinity. We will have e to the power minus y, and then dx is 1 by n y to the power 1 by n minus 1 dy. Now take 1 by n out. We see that this is just the definition of gamma function. Yeah. So now this is just the definition of gamma function, and this is equals to 1 by n gamma of 1 by n. Yeah. Basically this is 1 by n factorial. So for any n, the answer will just be 1 by n factorial. So basically for the first case we will have 1 by 1 factorial, and this is just 1. Now for this is just 1 by 2 factorial, this is just root pi by 2. Now for others, we know this is 1 by 3 factorial, 1 by 4 factorial, 1 by 5 factorial. But how do we find this? Like, this is just a notation, and this isn't really a perfect answer, because this one is a perfect answer because we can find its value. Yeah, but this one, like, how do we find 1 by 6 factorial? That's the question. Okay, actually, yeah, this question is just modified to the other question. We haven't yet really got the solution. Yeah, so now if you are having the same doubt about how to find these values, now I will introduce you to a series expansion for gamma function. So basically we have a Lorentz series expansion for gamma function, which is something like this. Basically gamma of g is equals to 1 by z plus Euler-Mastroianni constant plus Euler-Mastroianni constant square plus Riemann zeta of 2 by 2 factorial times z plus minus Euler-Mastroianni constant cube and then sorry again minus and minus Euler-Mastroianni constant pi square by 2, and then minus 2 times Riemann zeta of 3, which is a Paris constant, by 3 factorial times z square plus big O of z cube, because this will be somehow more smaller and that's why negligible. Okay, so now I have derived this series already in one of my videos, which is over here. Yeah, and now using this we can write the expansion for 1 by z as well, which is z minus Euler-Mastroianni constant plus this will be Euler-Mastroianni constant square plus Riemann zeta of 2 by 2 factorial times 1 by z plus Euler-Mastroianni constant cube minus Euler-Mastroianni constant pi square by 2 minus 2 times Riemann zeta of 3 by 3 factorial times 1 by z square. Yeah, and then plus big O of z cube. Okay, so now we have this series expansion. Yeah, okay, no, not of z cube, sorry, 1 by z cube. Okay, now if z is somehow big, yeah, if z is somehow a bigger value, in that case this will just go to 0. These are just going to 0. Yeah, so we can say that gamma of 1 by z is approximately equals to g minus gamma. You can also check these values. Yeah, these are going to 0. If you try to find let's say gamma of 1 by 5 or gamma of 1 by 6 or such values, you will basically get that this is 4.5 something because our Masonic constant is 0.577. Is this the same, yeah. In 1 by 6 this is also 5.5 something like that, yeah. So basically this approximation also works for somehow bigger values of g, and this actually works if g is going to infinity. If g is going to infinity, gamma of 1 by g is actually equals to g minus Masonic constant. But for these values also you can use this approximation to get the values. So that's why now for every g we are able to find gamma of 1 by g, and after we have gamma of 1 by n, then just multiply by 1 by n to get the 1 by n factorial. So that's how we can solve for approximated values of all these integrals. And yeah, so if we have solved for n, that means we have solved for every possible integers that I have given over here. So that's how we solve this integral. Hope you enjoyed the video and also learned something new. Hope it was fruitful. Thanks for watching and look forward to seeing in the upcoming videos too.